currents, opposite basically to whatever you have for NPN. And the model for this, I'm going to draw it upside down, is like that. So you have your emitter at the top, base here, collector here. Same equation for IC, and this is your VE. Because inside this guy we have two little diodes that are facing this way, as shown here, and inside the PNP we have two diodes that are facing the opposite direction, right? And we saw that all the equations are the same or very similar, and then the second analysis based on this one or the other one really isn't that different. One thing we noticed is that, like diodes, if you want to use the physical model, if you want to use this nonlinear relationship between the current and voltage for your device, your equations will take a little bit of time to solve. But we also remember from the diode discussion that the voltage drop across the diode when it is on has a very limited range. For measurable currents, it's somewhere between 0.5, 0.6, 0.7, 0.8, somewhere in that range. It's a relatively small range of values for that VE on. Same thing applies to PJT. You have two diodes, same issue, right? So for a device in active region, we have VE forward biased and VC reverse biased. NPN or PNP doesn't matter. Right, so this is a device in active region. So therefore, for the base emitter diode, we expect about that much voltage drop. You expect about 0.5, 0.6, 0.7 volts of voltage drop across the base emitter junction. Base collector, you can't say anything, right? Because base collector is reverse biased. In theory, it can take any voltage on it, right? And then the current, if it was a diode, would be IS. If it is a transistor in this configuration, the current through that diode is set by that expression over there. Or beta ID, right? Same thing. Or beta ID. So, I expect in this case to have a VBE that is on the order of somewhere in the range of 0.5 to 0.8 volts. Right? 0.5 for a big fat transistor, 0.8 for integrated transistors. For the ones that you use in the lab, they're somewhere in between usually. So 0.7 is usually a good number. 0.6, 0.7. Okay, so we use 0.6 for the diodes, about the same number, 0.7 for BJTs. A common number, the number that actually helps you with most of these diodes is typically 0.7 for discrete BJTs. So VBE on is around 0.7. For diodes, they're a little bit bigger than BJTs, we use 0.6. At the end of the story, it's only 100 millivolts difference, right? And the voltages that you typically have in your circuit are usually on the order of volts or more. And then if you assume that, life all of a sudden becomes much, much easier. So for example, let's do a PNP because we've solved the fewer PNP transistor examples. So let's say okay, and I can ask you what is IC in this circuit. And then knowing that, let's say beta is 100, and okay, so what is IC? Okay, beta is 100, and now instead of giving you IS value, I can give you what is the VBE on, right? So again, by looking at the problem and what information you have, you can decide which model is going to work best. Let's say we assume that VBE or VEB, because this is a PNP, VEB on is, let's say, 0.7 plus. Okay? And I want to find IC. So normally, and then you've done this a few hundred times by now, normally your approach is to write a KVL here and use the device equation to solve for IV or IC or whichever parameter that shows up. So if I write that equation, it's going to be my KVL is 5 is equal to IERE, so that's IE times 1K plus VEB, right? It's the emitter base voltage. Plus, and then remember that ID goes up, so ID times 300K. Okay, so that's my KVL, and I know that IC for the device is IS into the VEB over VT, right? So this is the equation we used before. And then I know that IE is IC over alpha. I have beta, so alpha is beta over beta plus 1. I can find beta. I can find alpha, so I plug it in here. And then IV is IC over beta. Right? So I could solve that equation if I wanted to use the physical model. But usually you needed a few iterations. If I assume this VEB is fixed, then life is easy. I have one linear equation that says phi is equal to IC over alpha. That's for my IE times 1K plus 0.7 plus IC over beta times 300K. And this gives you IC value. Right? So I just have one IC, simple linear equation done. And if you choose the right value for this VDO, if it is a small transistor, you can pick between, I don't know, 2 fingers, 0.6, 0.7 is good enough. If you need to use 3 fingers or maybe a hand, maybe 0.4, 0.5 volts, right? If you can't see it with your eyes, 0.8 volts. If you use the right value for this VDO, or if you just read it off the data sheet, this number is going to be within a few percentage points of the actual value. And then you don't really need more accuracy than that. Because whatever resistor you choose has a tolerance. Whatever power supply you choose has a tolerance. The transistor itself, we haven't discussed it much, but beta, we assume 200, but if you look at the data sheet, they usually give you an upper or typical value and maybe a minimum value, but there's no upper value. So they say the minimum is 100, typical is 250, there is no high upper bound for that. It can be 300, it can be 350. There is a lot of variability for beta for a given single transistor. Different currents for the same transistor will give you a different beta. Good news, it's a function of temperature too, right? So there's really no need to get anywhere closer than 5%, 10% of the actual value. Beyond that, you either do simulations or you make the device and do a measurement, right? And then actually we're going to learn about circuit techniques that are tolerant of those variations. So variations in beta do not affect my circuit that much. Or variations in R's do not affect my circuit that much. So you come up with some circuit design techniques to fight those issues. Okay, so that's that. And then with this knowledge, you can solve all of the problems that we haven't on the assignment. I think it's just one. Now, any questions? Easy peasy. Next topic. We talked about active region of operation for transistors. We said this is where we keep it or keep them most of the time in analog electronics. Cutoff is everybody's favorite because you just ignore the transistor, you're done, right? But there's one other region that we haven't discussed, and it's saturation. So I'm going to switch back to NPN. Everything applies to PNP as well, right? So I'm going to talk about the diodes and what happens to the diodes. Same thing happens to the diodes in the PNP. So I have two little guys inside. And structurally, I know that this is how this device is made. So at the top, I have an N region, in between I have a P region, and at the bottom I have another N region. But because of the way these devices are made, I don't have two exactly similar diodes at the top and bottom. The diode between base and collector is a little bit different than the diode I have between base and emitter, right? So this is base, collector, emitter. So this bottom diode, the emitter diode, usually has its N side a bit more highly doped than the diode on the collector. Because of that, if you pass the same current through these two diodes, they will have different VBs. It's like they have different ISs, right? Two diodes, almost the same, so it's not exactly. Usually the base emitter diode is a little bit smaller as well, which actually, again, contributes to a higher VB on. But for the same current through these two diodes, you get a slightly larger VBE than VBC. So if VBE on is 0.7, VBC on is 0.5 or 0.6. A little bit less, right? But it's noticeably less, 0.1 volts, 0.2 volts, right? You don't get exact same values. And then among these different operating regions, we said saturation refers to the case where BE diode or BE junction is forward biased and BC junction is also forward. So, or it is becoming forward biased. So you have some voltage drop across the base collector region that the diode, the base collector diode, which so far had a reverse current going through it, it starts to push a little bit of current in the other direction. So what happens is that as the transistor enters saturation, remember IC is marked this way. As a transistor, let's say that is happily in active region, for whatever reason, it is entering saturation. The first thing you notice is that you notice IC is becoming larger or smaller. So that's IC. So you're measuring IC. As the transistor enters saturation, will IC become larger or smaller? Smaller, right? Because you're pushing current in the opposite direction. So if you had like 5 milliamps of current going down, now you're pushing 2 milliamps going up.
Well, yeah.
Right? So it's 3 milliamps now instead of whatever it was before. And so that's the first thing you notice, that you notice IC is dropping. The other thing you notice, if you're careful and if you have 5 instruments attached to a transistor, you notice that the ratio of IC to IB is changing. Ratio of IC to IB, if the device was in active region, was your beta. It was a large number. But now, your base collector diode is conducting, two things happen. IC drops, because you're pushing a little bit of current in the opposite direction, and IB increases, because where does that extra current come from? It's coming from base, right? So your IB goes up, and your IC starts to drop. So if it is not fully saturated, you're still not too sure, but you do a calculation and you see IC over IB is 50 instead of 250. But something will come wrong, right? If it is 10, if it is close to, if it is less than 10, definitely something is going on. But yeah, if it is significantly less than whatever the data sheet says, maybe your device is saturated. You really shouldn't be measuring currents to detect saturation. As engineers, as electronics engineers, we like to measure voltages. Measurement of currents is a pain. So we like to measure voltages and then see if the device is saturated or not. If the device is in saturation, I have a voltage drop across this diode and a positive voltage drop across that diode. So VBE, let's say a typical off-the-shelf device, is around 0.7 volts. And VBC, because we said it's a little bit different, the diode is a little bit different, but it is on anyway. VBC is on the order of 0.5 to 0.6 volts. Somewhere in that range. So whatever base voltage you have, collector is about half a volt, 0.6 volt below that, emitter is about 0.7 volts below that. If you look at the collector emitter voltage drop, the voltage drop between these two terminals, VCE, right? So if you can see it already from here, but VCE is VC minus VE. Okay? I'm going to write the equation, then I show it to you on
Oh, that
graph.
makes sense.
So I added VB and subtracted VB here. So VB minus VB. So VB, let's say minus VB plus VC plus VB minus VB. Right? This VBC. So this is VCB minus VB. And if the device is saturated, this is about 0.7 volts, right? And VCB or minus VBC, right? Let me write it up. Minus VBC. This is minus VBC, right? That's about 0.7 volts, and this one is about 0.5, 0.6 volts. So VC saturation turns out to be around 0.1 to 0.2 volts. This is usually how you can tell if the device is saturated or not. Because, and the reason that we like to do this instead of measurement of currents or base voltages or anything else, is that, and we'll talk about it next lecture, but base is a high impedance node, right? So if you look at the examples we've done so far, the resistors you have in the base circuit are usually big. You're talking about tens of kilo ohms or hundreds of kilo ohms. Resistors you have on the collector side or emitter side are usually much smaller. Kilo ohm range, hundreds of ohms, right? We'll see why that is. Or you already know why that is, because in the base current you have beta times smaller currents. So you need beta times larger resistors to maintain the same amount of voltage, right? But base is usually a high impedance node. Measurement of voltages on a high impedance node is tricky because your typical multimeter has a 1 mega ohm input impedance. 300 kilo ohms of resistance there, you put it there, 1 mega ohm is comparable to 300 kilo ohm. Your instrument affects your measurement, affects your circuit, changes the voltage at that node. Your circuit that was happy before you touched it may become unhappy. Or you think the circuit is saturated, you put your probe there and everything is good. You remove the probe, it's saturated again. Measurements on high impedance nodes are tricky. You have to have the right equipment for it, or you have to know the limitations of your instruments really well before you try. So I try to avoid measuring base voltages, if I can. Right? Collector and emitter, much easier. So I can easily measure the collector voltage, I can easily measure the emitter voltage. If I do that, and I measure something on the order of 0.1, 0.2 volts, I may be in trouble. Unless saturation is what you want. Right? And that's saturation. So when your device saturates, you have a few things to check for. One, VCE is small. You're getting close to 0.1, 0.2 volts. And it's not VC or VE, it is the difference between them, right? Second thing, base current usually goes up quite a bit. So you design the circuit for 10 microns of current, all of a sudden you notice, maybe hundreds of microns or milliamps are going into your base. If you're measuring two currents, ratio of IC to IB usually becomes worse. If you're making an amplifier with this circuit, usually your gain drops when it enters saturation, right? Or it's getting close to saturation. If your power supply is limited, right? So let's say you're making a circuit that should work off a 1.5 volt battery. You don't really have a lot of room. up there. It's a 0.7 volts just across VBE. What does that to do anything else? So what they usually do is that you make design very close to the edge of saturation. So maybe you forward bias that base collector junction by 0.1, 0.2 volts. Not all the way to 0.5, but a little bit. So that you can use that voltage headroom a little bit more effectively. And remember that for diodes, essentially you wouldn't measure anything until you hit 0.4, 0.5 volts, right? So that can happen. Your device may be in soft saturation. It still works, it's still doing its job, but you don't really have a lot of headroom. Because as soon as that voltage goes up, if this diode is forward biased by 0.2 volts, as soon as your signal at the collector is 0.3 volts, it pushes the device into deep saturation, then you're in deep trouble.
So you're saying like you sometimes want to operate near saturation because you want to use all of the sort of voltage you're given in whatever circuit you're making, so you want the voltage drop across these to be small as possible, right? Okay.
So, but if you don't have that limitation, if you have, you're using a benchtop power supply, or it's none of your concern, somebody else has to worry about it, you don't go below 0 across the base collector. So if base collector is 0, again, I say that's edge of saturation. I don't push the device I don't forward bias like that at all, if I can. So at that region, if that's 0 and this is 0.7, your VC is about 0.7 volts. Right? I don't make it less than that, if I can. If I really, really, really have to, maybe I can lower it to about 0.3, 0.4 volts. But then after that, you're going to see distortion. Okay, so that's saturation, right? And if you take your typical BJT, and let's say, let's just do it on the phone. Let's say I apply a base emitter voltage here, and a base collector voltage here. So this is the ground, this is VE, and this is VC. And I measure my collector current. And we'll see why the collector current is important, but you already should have an idea why it is important. Because remember, this is my controlled source. This is where hopefully all the interesting stuff is going to happen. Right? So IC is usually the desired output, or the one that gives me more information about the stuff that is going to happen. So if this is the case, and I start to play with these two voltage sources, I can see a few things. So first of all, let's say the device, you put a VC of 1 volt, 2 volt, something, to make sure the device is not saturated, and then you change VBE. And what you expect to see is something like this.
Get a wireless charger.
Right? This is your exponential relationship between VBE and IC. But you have this other variable. So let's say you choose some value here. Let's say you choose this value. You say, I'm going to bias my transistor at that current. Some VBE gives me some IC. And if you set the value of base emitter source to be that much, and change VCE, then ideally what you expect to see is this. Right? If the device is in active region, you don't want to see a change in IC. When you change VCE, it's a current source. Shouldn't care, right? But as you drop VCE to small values, as you go closer and closer to 0, let's say the threshold is somewhere around 0.1, 0.2 volts, then you start to see a drop in IC, and eventually it gets really close to 0. And then this is for, let's say, VBE1. And if you choose a larger VBE, you obviously get a larger current, but same thing happens if you drop VCE too much, right? So this is the ideal curve that you expect to see for your transistor. Constant IC that doesn't depend on VCE as long as the device is in active region. But once you hit a VC of 0.1, 0.2 volts, you start to see a drop in AC. And that's your saturation. So to the left of this curve is your saturation region, and to the right is active. Okay. Any questions? Everything is so easy. Let's look at that curve one more time. Okay, so we just said that different values of VBE, so this is VBE1, let's say, and this is VBE2 larger than VBE1. We'll give you different values of IC that do not depend on VCE. Oh, that's in an imaginary world, right? That's if you have the Apple Vision Pro. In real life, that doesn't happen. In real life, what happens is that we will have a little bit of slope to that IC curve. As we increase VCE, IC increases a little bit with it, right? So instead of having a straight line here, you get a little bit of slope here. So this one actually already has a little bit. Okay? So in reality, you get something like this. So for a large VCE, you get this much larger current. Not that much, a few percentages. Right? So you go from 1 volt to 10 volt, especially for big transistors, off-the-shelf transistors. The difference is 2%, 3%. You probably won't notice if you don't look there, right? And this is called early effect. Early is the name of the guy who first observed it and modeled it. And interestingly, if you go and continue drawing these lines, they all cross this VCE voltage at the same point. These VCE axes at the same curve. I should have done a better job of it. They all cross this VCE axis at the same point. It's a negative point, it's a negative voltage, and this is called an early voltage. So this VA is your early voltage. And early is a name, so E is always capital. This early voltage for your typical transistors off the shelf is 100 volts, 200 volts. It's a big, big number. So a couple of volts of change here in VCE, you will not see that change in current. Right? For small integrated devices, it could be 5 volts. So you have a bit of a problem. You see that change in current with voltage quite more significantly to devices small, but big devices, large devices, you normally don't care. And because that's the focus of what you guys are learning, I'm going to leave it there. So usually you take into account the early effect for small signals, when you're making amplifiers, all that stuff. If you're making amplifiers with off-the-shelf transistors, you don't care. It doesn't affect you. The equivalent resistors that you put in your model are really not going to improve your accuracy very much. Okay, that's that. Any questions? So early effect, this is as much as we need to know about it. Just know that the current doesn't stay constant, but you're going to have a hard time measuring it. Oh man, we did everything we wanted.
Tutorial.
Let's go home. You paid for this.
Sorry, I just need clarification. Why does the voltage increase, or sorry, the current increase as
Good question.
you go on there?
Short answer or long answer?
Long.
Long.
Doesn't matter to me. Just need an answer.
Okay, well let me give you
Laying answer.
one answer in between. Short answer, it is what it is, David.
Okay.
A little bit longer. Remember that you have two junctions, N here, N plus here, P here, right? For each junction, you have a depletion region. So you have a depletion region here, and a depletion region here, and then one at the bottom. So in depletion region, you have negative fixed charges here in the P side, and negative positive fixed charges on the N side, right? Now, remember you had something called beta, the current efficiency. Beta was the ratio of the collector current, this IC, to this current IE, right? So that determined, or that told you when electrons are injected into the base from the emitter side, how much of them will get to the collector side. So that's alpha, that was really the number. Alpha told you the efficiency. If it is 0.99, it means that you lose 1% of the electrons that are injected into the base, but the rest of them will end up at the collector. Now, to increase beta, what did you do? You make the base narrower and narrower. If you half that distance, your alpha, or the number of the charge carriers that will go from here to the collector, increases significantly. Okay? Now, why does we have the area effect? When you put remember the top diode is reverse biased. When you put a larger reverse voltage across that diode, the depletion region width increases.
Wait a minute.
It's as if you have a smaller base. It's as if your beta has increased a little bit, right? In a big device, that difference doesn't matter much. In a small device, integrated device, we're talking about nanometers, about tens of nanometers, and a few nanometer change will make a big difference. In a big device, you probably have a little bit more for that. Okay,
Yeah.
that's kind of the
Thank you.
in between answer. No break today, huh? I'm doing all the time.
What?
I want to show you an interesting circuit.
Okay, just a second.
Okay.
The good answer here is that all circuits so far have been interesting.
It's this one. No, it's not.
Okay.
Oh.
Let's look at this circuit.
Well,
This is a really interesting circuit. Two resistors actually you can do it with one, and then one transistor, and it does so many things.
yeah.
Let me write my KVLs in case. Or just KVLs. So I can write a KVL at the input node. I want to see what happens, so let me tell you the problem first. I want to see what happens to V out when I change V in. Okay, so V in goes, let's say, from 0 to VCC. I want to see what happens. So let's just formalize it. So plot, V in, V out, characteristic curve. When V in goes from 0 to VCC. Okay? So transistor is a typical transistor, some VDE on, some VC saturation. So you assume the VDE on for the device. Forget about the physical model, right? And some VC saturation for the device. When you read it, let's say VDE on is 0.7 volts and VC saturation is 0.2 volts. You read them off the data sheet. And let's say maybe a beta of 100 or something. Okay? So I want to see what happens to this device as I go from being 0 to being equal VCC, and I go slowly.
My
So
guess
nothing
is I should.
time dependent is going to happen. So let's see. V in equals 0. What do you think the operating region of the transistor is going to be? So I have my two video guys here. The base collector diode and the base emitter diode. And VCC is positive, right? So let's say VCC is 10, whatever. Positive. Positive and significantly larger than VBO. 2 volts, 3 volts, 5 volts, 10 volts. So Vin equals 0, what do you think is the operating region for my transition? So I may have 1 volt per item.
It should be off.
It should be off.
Off, right?
Right? Yeah. 'Cause
Yeah.
there's no current.
Because I don't have enough voltage to turn this
It's
guy
there's
on.
no
This guy will not turn on,
which means it has
and
to.
that guy is happily reversed bias.
Yeah.
Vin is 0. Vin is
So
0.
it's just
So at 0 volts, I don't have enough voltage to turn this guy on. I can write my KVL, doesn't give me change anything. But let me write my KVL because it applies to what is operating region. So my KVL says Vin is equal to IBRB plus VE. Right? And at the output, I have V out is equal to VCC minus ICRC. These two are independent of the device, independent of operating region, all that stuff. These are voltage drops of cables. So with the V in close to 0, actually V in less than VB on, right? For V in less than 0, this diode is off. Good news, this is the favorite operating region when you solve problems. Then what happens to IC?
0.
IC is 0, right? So let me write the whole thing, but you already know. So VE off means reverse bias, and VC is happily off as well. You can verify this later after you have the currents calculated and everything else. And therefore, you can say that all terminal currents are 0, including IC. And if IC is 0, what is the out?
0. Field. BCC.
VCC.
Yeah.
Right? Good. So, and that stays the same. For as long as V in is less than, look at this equation. As long as V in is less than VBE, I cannot have a positive ID. Right? So or the diode is not on. The junction is not on. So this stays for as long as V in is less than VBE on. Right? But then V in becomes slightly larger than VBE on, then what happens? V in slightly larger than VBE on. So let's say VBE on plus, 50 millivolts more, 100 millivolts more, whatever that you need to turn on that diode. Then you expect the base emitter diode to turn on. But I can make this go into saturation in this map, right? I'm not going to do that. So let's say reasonable value for RC. This diode, VC diode, will remain reverse bias, right? So if you have, let's say 0.7 here and 10 volts up there, maybe it is 9, maybe it is 8, maybe it is 7, but it stays off, right? So you'll be in active region.
Okay.
So after off, you enter active region.
I don't know what you said.
Meaning that B is on and BC is off. And what happens now is that in addition to those two equations, which are from KVL, from your circuit, you have a device equation. That IC is equal to beta IB. Right? And then therefore you can quickly calculate V out. So combine those two equations and you can see that V out is equal to VCC minus, for IC, well, I calculate IB from the first equation, so it's VB minus VB, Vin minus VB divided by RB, right? So that's V in minus VBE divided by RB. That's IB multiplied by beta. You get IC multiplied by RC. You get your V out. Right, same equation that I had over there. Okay, so this is for as long as the device is in active region. Let's just plot it and see how it looks like. How do we do it? Okay, so let's just do it on the side. So I'll do it on the side and then I'll move my plot later.
Just 7 plotted for.
So this is V out,
You can have both of them.
and this is V. So initially, for being smaller than
Leave it here.
V on, V out stayed at VCC, right? Once you go past VB on, V out starts to drop as you increase V in, right? Because
just like that.
how does that happen? Well, a larger V in here, larger ID, because this voltage is more or less fixed, it's 0.7 volts, right? So a larger voltage here, a larger current through ID, through RB, meaning a larger current IC. Larger current IC means that the voltage of the across the resistor gets larger and larger. So this top end of the resistor is fixed, this end must go down. So what you expect to see, or what you see, is this. Right? As you increase V in, V out starts to drop. How far?
Yeah.
Look at V out in this circuit. V out is your VCE. You know there is a limit. You cannot, enter saturation and go keep going. Right? So this bottom end, at some point you hit VCE saturation for V out. At some point you hit that. Okay? So there is a VCE saturation that at some point you will hit. And after that, you expect the output voltage to not change anymore. You get your 0.1, 0.2 volts. That is the difference between the general voltages of these two dots. At some point, you'll get there, and then it will stop responding to the gain. Okay? The more you increase gain, what happens is that we increase IB, you push a little bit more current up here, but this is already on. Okay? You just increase IB, and then if you increase it too much, the rest of it will go to the meter. Your output voltage will start responding to your input voltage. Okay? Alright. So that's my. So at some point that will happen. I cannot really tell you when it happens because I should have values for RB, RC, and VCC. But if you go and calculate, if you have values, you can plug it in here and see when this becomes equal to 0.2. And that's the goal. But look at this. Okay, this beautiful.
No.
Tell me what is happening here. So, well, tell me why I like this circuit. Other than, it is simple. It's doing something interesting, right? It's doing something that you shouldn't have seen so far.
Shouldn't?
Have you seen something like this?
Is it cutting off?
That's one
The
thing.
limiter?
No? So, have you ever seen a circuit, a linear circuit? Not time dependent, no phasing information, right? Where you increase the voltage here and the voltage somewhere else decreases. That never happens.
Wait a minute. Oh no.
Well, if you want to cheat and say a transformer, then you put the dot outside it. That's transformer doesn't look at DC.
I wasn't gonna say a transformer.
But DC changes, right? So you increase the voltage a little bit here, and somewhere else in your circuit, the voltage decreases. That's really interesting. That's the first thing. that should make you interested in this circuit. But right away, you should be able to see something else that this circuit does that you haven't been able to do. Assume Vn is the digital voltage. It only has two values, 0 and 5. Let's say VCC is 5. What is the output? So you apply 0 to the input, what is the output? VCC. You apply VCC to the input, what is the output? 0.
Saturation.
Yeah, you can just plot. 0 logic, right? So you apply 1 to it, it gives you 0. You apply 0 to it, it gives you 1. What is it?
It's a flip flop.
It's an inverter.
Yeah,
Inverter. Right? So this is a gate. This is a logic gate for you. One transistor, done. So this is how you make an inverter. For an inverter, you don't like to have a lot of transition region between, the
Slowly repeat that.
1 and 0 states. You make this really steep, but this is what it is.
So this is called an inverter,
Yeah.
but I can also go to the store and buy this thing that turns 12 volts into 120 volts AC, and that's also called an inverter. Is that the
That's
same
a,
thing?
no, that's a power electronic circuit that they call inverter. It's not
Okay.
the same. So this is an inverter from the logic.
Logically.
Yeah.
Standpoint. So the inverter in logic gates is something that turns a 0 into a 1 or 1 into a 0. Right? It's that bar that you put above A's or B's or C's. And this is that device or circuit that puts the bar above A or B or C or L. So already it does something I haven't seen before, and it does actually something useful as well. With diodes, you can make AND gates and OR gates. You could never make an inverter with diodes. Now you can make an inverter. You can make anything you want. You can make any logic circuit that you want, any CPU that you want. You can make it now with a bunch of diodes and a few transistors. Done. Right? So this is where the digital people start. They didn't progress after. But, okay, so let's take a break, 5-minute break. I'll show you why I like this circuit is more.
What are we sponsored by?
It's more interesting.
This is like this
Should I say that?
Huh?
Should I say that to the
Better
recording?
style.
You gotta fold this in. You
Andy, can you explain what he just said?
So what do you mean?
Like, explain that. Like, okay, so when that VN
Yeah.
is less than VBR, you just have a saturated diode.
Yes.
So is it? So this is my top. Yeah. So is my current going through this way? It's going through this way. Okay.
And there is a VCC here.
Yeah.
That could be positive or negative.
Okay. And then so
Right.
when this diode turns on,
Yeah. Basically, it means that none of the current goes through here and
oh, it's just a-
goes around there. Because that's easier to pass. VCC is
yeah. And then at what point when does it flatten out at?
at this so like this is the BE saturation.
Yeah.
So that's saying once it's greater than the voltage drop across that ground, then all the current is going to go through there. It's going to be a flat.
What?
We don't know. There's just some VN that is. Yeah, when it's approximately the same as saturation, that's when it's
You're assuming So
Bro. An average.
Yeah, that's what happens. You can see the answer to this question. But data sheets sometimes use the data sheets to very small. Okay, guys. For the second lap, think we're doing it from tomorrow. I have put the data sheets for all of these devices on campus. You can go and search, right? But sometimes different manufacturers show you information in different ways. If you check the ones that are already on campus, you should be able to answer all those questions for your opinion, right? But yeah, you can. These are old devices. These many manufacturers for each one of them. All right. Let's get back to our lecture.
I already had one, but thank you. You just saw the ad. But I think you wrote that on.
Matthew cannot.
Actually, one small note here. So in here, we assumed the constant voltage of 1, right? Because we wanted to calculate less,
Here.
right? If you use the ideal dial, if you go and simulate this circuit, if you go and check it in the lab, it's going to be more or less like this. The only thing you see is a little bit of rounding around these edges. These corners are not going to be super sharp, right? Because the dial turns on or off slowly. That's the only difference. But more or less, it's going to look the same. So again, you are not losing much if you use the constant voltage model. But I drew this again here. And let's look for other reasons that this is an interesting circuit. So if the device is in active region, assume active, right? So assuming active means that Vin is large enough to turn this junction on, but this guy is still off. Or this is forward bias, that guy is still reverse bias. So I'm in the active region of the device. So BE on meaning forward bias, BC off meaning reverse bias. Doesn't mean the current is zero. Then we actually tried the equation for it already, but let me just do it again. V out is going to be BCC minus base current was V in minus VBE divided by RB multiplied by beta. This gives me IC, and ICRC is the voltage drop across RC. And so that's V out. Okay. So the device is happy here. I biased it. So if you look at the input output relationships for ICVCE and ICVBE, this is your ICVBE, and this is your ICVCE. So this is the curve, let's say, and this is your bias point. So you bias it at this VBE naught, whatever that is needed, gives you some IC naught. And you have some VC for biasing that puts it well into active region. You're not too close to the saturation. I have bias. This is called bias. Right? I put my device on the DC conditions where there is no fluctuations in, let's say, power supplies or inputs and temperature. I put it where I like it. What does it mean for BJTs? It means that I set IC and I set VCE. I go and choose my VDE naught such that I get the IC that I need and I'm far enough from the edge of saturation. As far as I can be, depends on the problem, right? But that's biasing. I set IC and I set VCE. This is biasing. This is when I say my transistor is biased, it means that I've already thought about those stuff and I chose proper IC and proper VCE values for whatever application I have in mind. So I biased this device and I'm getting that.
So essentially, you can use this relation to get whatever IC current you want, as long as it's from like some edge of saturation off of whatever you're.
How we choose IC depends on a few factors. Usually, the most important one is gain. How much gain you want from this amplifier? We'll see.
Okay.
We'll see. You know, in Actually, next week. Next week we're going to talk about all amplifiers and
There
filters
is
and
no
all.
next week.
But IC sets your gain usually.
Okay.
So that's one thing. The other factor that there's many actually, so that I mentioned. The other factor that is important when choosing IC is your power consumption. Because the amount of power you're using in this circuit, ignoring IB, is your IC times VCC. If you have a battery and you want that to last a long, long time, you want to choose a small IC because VCC is not going to do it, right? So power and gain are usually your first considerations for choosing an IC. VCE depends on how much variation in voltage you expect here. If you don't expect this voltage to change much, put VCE close to zero, close to your saturation. If you think the signal here is going to go up and down a lot, then maybe you want to choose a higher voltage for VC. So it's called voltage swing. Swing determines your VCE, gain, power, sometimes noise determine your IC. But they come from somewhere else. The values of IC and VCE that you need. We know somebody told us, requires the device when it is happily in active region, and I have that relationship between input and output. Okay. Now, with that relationship, if I see how sensitive that output is to the input, if there's a small change here, I want to see what happens to the output. What I can do is that I can take the derivative of that with respect to V in, right? So dV out over dV in. Small change at the input, what does it do to the output? It's going to be, well, VCC is a constant, goes away, 0 when I take the derivative. VBE is more or less a constant as well, right? It goes, because if this VE changes by a few millivolts, that's going to change by a few microvolts. So that's also constant, doesn't depend on VE, so that's also 0. So all I have left with is minus beta small c over small b. Right? Anything interesting here? I love this result. How come you don't?
We don't know.
Again, think about values that we had. So for RB we had 10K, 100K, something like that. RC we had 3K, 4K, 5K, right? So this ratio is 5K over 100K, let's say. But we have this beta number in front of it. This number, beta RC over RB, we can easily make it larger than 1. We can make it 100, we can make it 1,000. Right? Choose RC to be 10K, beta is 100, so that's already a million. If you want to gain of 1,000, choose RB to be 1K. You can get gain out of this thing. You can have a small change at the input that shows up as a big change at the output. Small change at the input can be your signal, your microphone, your temperature sensor, your antenna, whatever, right? The small signal comes here and tickles this big event. You get a big signal at the output, and you control how much. Beta comes from the device, you don't really have much control over that, but 200, 300 something, right? RC and RB are your choice. You choose these two. You choose RC to have the VCE that you want, and you choose RB to have the IC that you want. You can get a large gain out of this thing. Easily 10, 50, 200, whatever you want, right? Not whatever you want, but if you're reasonable, you can get a good amount of gain out of it. The only issue is that, and some of you may be picky, is that the gain is negative. What does that mean? It means there is a 180 degree phase shift between input and output. Input goes in, goes up, output goes down. Input goes down, output goes up. There is a 180 degree phase shift between these two. But who cares? For most applications, we are not that phase sensitive. There are some applications that we have to do. But most applications, 180 degree phase shift doesn't make a difference. Right? So you have an amplifier. One transistor, and actually, that's all you really need. One transistor, a little bit of DC at the input, a little bit of DC at the power supply. Just pick a couple of resistors and you have a good amplifier. Any questions? You're all loving it, huh? So when you go to the lab, this first lab is about DC. BGT is a DC. You know, once you're done with the lab, play with it. See what happens to the output. You know, especially the collector is usually your most responsible output. See what happens. To collect the voltages, to collect the currents, and okay. So we have an amplifier. So we're getting into this amplifier section. Let's just start the discussion. Actually, you know what? Let's do the amplifier thing next week.
Where there is no next week.
We are not going home. Let's talk about biasing. Yes.
So there is no next week. Next week is reading break.
I'll be here. You can go. Next week is reading week?
Like it is, right? Like how does
Yeah,
like,
it is.
how is it?
This is just the website is trolling.
Then we have to squeeze everything into the time we have. Let's go.
Victor.
Okay. So I'll talk about amplifiers after we come back from break. Let's talk about biasing. Okay. So let's talk about biasing. So what does biasing mean for PJTs? And then designing with PJTs, NPN or PNP. Biasing refers to setting IC and DC for your device. Okay? And then actually on this curve, you should be able to see the importance. Let me go up here on this curve. Bias, so what is happening? I'm putting my device, let's say, with this IC, I bias it with this IC, or this VBE on, it's going to sit here. And it's going to have that slope, that negative slope that we just talked about. You know what, let's use that graph and show one more thing here. Input output characteristic. Okay. So it's like this. So let's say your V in, you bias it initially around here. That's your biasing point. That's your Q point, quiescent point, right? Operating point.
Here.
That's where you set everything at the beginning, and then your input signal comes and looks like this. So let's say this is your input. It's changing around that bias point, right? So I'm not changing the operating region of the device, right? So let's say this is, I don't know, V in of 1 volt, this is 10 millivolts.
So what do you say biasing? What exactly are you referring to?
I'll come back to that in a second. So it's
Okay.
setting IC and VCE.
Okay.
So DC conditions.
Okay.
I keep my device happily in the active region. If there is nothing coming up, no external factors. My device is happy in active region. Parameters are IC and VCE. But biasing means that the device is in active region. You don't bias a device that is saturated or in cutoff. Okay? Biasing means the device is in active region and you have your IC and your VCE on that device. So your input is changing a little bit here, and well, this is the input output characteristic here. We can map it, we can use this curve, the characteristic curve, to see what happens to that input. So as the input changes, let's say in this range, you expect the output to change, let's say, in that range, right? So and then it has this 180-degree phase shift. Right? So your input goes positive a bit, your output goes below where it is. And things look okay and nice. However, you could have gone and chosen this as your bias point. Close to the saturation, close to the edge of saturation. Right? You could have picked this as your bias point. So if you do that, so if you choose this as your edge of, as your bias point, then you have again a small change at the input. But this small change at the input, where is it? What happened?
Really?
This is magical.
Yeah.
Okay? So if you have that change at the input, then again map it onto this circuit, map it onto this graph.
They're not happening.
You're right.
So you have the baseline here, your output goes down,
Yet anyway.
hits the saturation limit, it actually is clipped, but then goes up and it's high. Goes down, hits the saturation, is clipped, goes up and it's high. Right? So instead of having a nice, well, sinusoidal that you have at the top, you get distortion. The bottom of your waveform is clipped. You lose your gain, your device stops responding to your input, right? So that's one problem at the bottom end of this curve. At the top end, you have a different problem. If I go and choose my bias point to be here, very close to the edge of cutoff, I have a similar situation but for a different reason. So again, if I map it, my output is okay when it goes down, but it's clipped at the top. Right? So you can have that clipping because of cutoff, because you didn't keep your device in active region all the time, and that's the device in the cutoff region. Or you can have it because of saturation. The voltage wanted to go so low that the device enters saturation. Right? The corrector voltage drops so low that the device enters saturation. Both of them are wanted. We want to avoid both, right? Because both of them, if it is an audio system, you'll hear it. If it is a video, if it is a video system, you'll see those of stuff on your screen. All those stuff can happen. This is usually why people don't want to buy your product, right? You want to make sure that you're avoiding those. This is distortion. Okay? You produce higher harmonics of these signals. We want to avoid distortion. So how do I do that? I choose the right VCE value for the expected output amplitude. If I know my amplitude at the output, if it is the output stage of a speaker, an audio system, let's say 10-volt supply, I want to deliver the maximum power to this poor soul. I want to use all of that 10-volt range, right? So I put my bias point exactly in the middle of that range. So I have the largest signal and the output without distortion. But if it is early, let's say right after this microphone, this is producing, let's say, microvolt of signal, it's going into, I don't know, some ATB afterwards. I don't need 10. If I get it up to, let's say, 100 millivolts, that's good enough for me. So what I can do is that I can bias my transistor down here.
You have so many.
Because you'll see in a second, if your device is down here, you get more gain out. So for gain reasons, you put your VCE here. But biasing, so again, different biasing. So you may use the same current, but you put different VCEs. You choose different VCEs.
Is this why microphones can peak? So like, if it's too loud, the microphone kind of just peaks. So is it because
That distortion, which one do you mean? The high frequency pitch?
oh no, just like
That's
if
because
it's
of
too
feedback.
loud.
So
Yeah.
clipping.
It's one amplifier in the chain of the amplifiers that is hitting with the top layer.
Oh, it is, right?
One amplifier in the chain. So it could be the very first one, which is, then it means that you
Yeah.
chipped out on the paying for the
Okay, so
microphone.
it is- I think it's-
Or it could be somewhere else in your audio system.
Okay.
Got
So
it.
it's one amplifier in that chain that is.
So you want
not
a
doing its
huge
job.
VCC.
But usually, if your amplifier is closer to these early stages in your chains of
And
amplifiers,
so a lot of
your signal is
microphones
still
that are
small,
condenser
right?
microphones,
you have,
you
let's
give
say,
them 48 volts.
you want to go from 1 millivolt to 10 volts. You need a gain of 10,000, right? So distributed between 4 amplifiers, let's say each one is giving you a gain of 10. So 1 millivolt goes to 10 millivolts after the first, after the second, it's 100 millivolts after. So 100 millivolts, I would put both of those amplifiers right here, very close to saturation, because I know the signal is not going to be large. But as I get closer and closer to my actuator, in this case the speaker, I want the largest possible signal. So I move my bias point closer to the middle of that curve. The range of that change at the output, that signal, the yellow thing or the blue is not blue. The yellow change at the output, that's called the voltage swing. So when they talk about voltage swing, it means the amount of signal, the amplitude of signal that we can have there without distortion. So if I tell you that I want a 5-volt voltage swing, it means that you have to be at least 2.5 volts away from cutoff and 2.5 volts away from saturation, because it's 5 volt peak to peak. I'll be clear,
Makes sense.
but it's usually a peak to peak value that I mentioned. So if I say 10 volt swing, it means that with a 15 volt supply, you want to be about close to the middle. If you bias at 7.5 volts, you're good. You're good. Okay, so that's biasing. You set IC for gain, power, noise reasons, and you set VCE for swing reasons. Swing and other amplifier parameters will determine your bias points. But then the question is that how do I do that? Let's say you've decided that you want to have a VC of 2 volts and an IC of 1 million. How do you make sure that happens? How do you make sure that, without the signal, it's just DC. But how do you make sure that your device will sit there and will not be too sensitive to a little bit of change in temperature in the room, or maybe switching transistor? If you make 1 million of a circuit, you cannot be too sensitive to your device parameters, right? If I switch the transistor, even the type of the transistor, I probably don't want to be super sensitive to it. So that wasn't before I got this. So let me add this maybe word here. In active region. Right? So it has to be active. To put the device in cutoff or saturation, it's the job for digital folks. It doesn't need a lot of brains. You want to keep it inactive. Okay, so let's look at a couple of examples. Tell me if you think these are reasonable biasing techniques. So let's say I already know this thing is an amplifier. I'd like to use this one. And let's say, so how many of you know that you can use this speaker as a microphone? A good number, right? Because a microphone, a speaker, you have a coil and a permanent magnet. You change the current in that coil and you produce a force that moves the cone, right? But if you do the opposite, if you move the cone using, let's say, sound pressure, you produce a voltage in that coil, across that coil, right? So you can use it as a microphone. So let's say I did that, and I went and made this circuit. Let's say this is the speaker. But it's the speaker that I'm using as a signal source. I'm speaking to the speaker. And let's say I have enough power supply here, and I've chosen the right RC to give me enough gain. And then my goal is to amplify the signal from that speaker. Because I'm going to get millivolts, and I want to amplify that. Will this circuit work?
At what? Because it'll
Why not?
You're missing R.
You're missing RB,
Yeah.
let me put RB back here.
Oh, that's right. Yeah, well, it's
Will this circuit work?
probably not.
Actually, by putting the RB there, you only reduce your gain, but that's a different issue.
In terms of the output of the speaker, you would have to overcome your diode.
Uh-huh.
So that means every time you go below 0.7 volts, you're gonna get,
Yeah, so if you're producing
It's
millivolts,
not
then
gonna
what
be
happens?
active. It won't be an active read.
it won't be active, yeah.
Your diode is not on, right? So, think about this as an AC source. Right? It's producing the signal for you. But your device is off. Right? You have all the components for making an amplifier, and you're screwing it up. So you're fired.
Wait, can't you just add the DC
Okay.
voltage? Series?
Okay, so the problem is that I don't have
Actually.
enough base voltage to turn this up.
Yes,
Just
right?
add
Add
more
a-
voltage.
So to save your job, you're gonna say, let me see, okay, you know what, I'm gonna bias it, give me another chance, here's your DC source,
We're not. What AC?
and, here's your RB,
Yeah,
and let me pull it up for you to DC. Your base emitter card is definitely on.
I don't know.
What's gonna happen?
It's just in the flat line.
No,
It's not on the other side now.
This time you got yourself killed.
Yeah.
Whoever that was running it before is now definitely gonna kill you.
well, it's not amplifying.
It's not, yeah.
Like if it's going through.
It's
If you look
just-
at the graph,
it's
on
gonna
the
be-
First problem you have
The same all the
is that
time.
you're
as
putting
DCC.
10 volts across the diode,
Yes.
or 5 volts across the diode, the base emitted diode. You toast that diode. If a firm really attached to that transistor, you
what?
get.
10 volts?
But let's say, for whatever reason, that doesn't happen. Right? So let's say you only use a VCC of 0.7 volts. You're careful.
So a voltage breakdown occurs.
You still don't get anything at the output. Why not? So let's say you're careful. You increase VCC very, very slowly,
There's no V out. There's no V out.
and this is the output. Happy? But you still don't hear anything. Yes.
Sorry, you said that 10 volts was a problem. Are we saying that voltage breakdown happens at minus 10 volts across?
No. If in here I didn't have voltage to turn on the base emitter, right? So you go and say, okay, I'm gonna apply voltage to the base emitter so that it turns on. I apply. If you apply 10, you toast the diode, you toast the transistor, right? Because the exponential relationship. You may not, but you definitely get yourself killed.
Yeah, the current gets.
Was it IS?
So
Yeah.
you outsmart that
I
guy
thought he
and
was
you
talking
start
about
from a
voltage
VCC
breakdown
of
voltage.
0.7 volts. 0.7 turns on the diode for you. Hopefully you're super careful, nothing explodes.
Yeah.
This still doesn't amplify for you. You get 0 at the output.
It's because it's on the right side of that graph, so it just flies.
No, I'm happily biased.
But isn't that
Maybe unconsciously. But I'm biased, right? So I am some IC, some VC SAS that is, let's say, 0.3 volts, 0.4 volts because the VCC is only 0.7. But you measure 0 at the output. Why? Come on, just because you're new to this. I'm tempted to put it in my face.
Please and answer the question.
Put a voltage source before the speaker. So when it goes through, the speaker would only accentuate that voltage source.
No, so this is the setup, right? So don't change. Why doesn't this circuit work? Why I have 0 change at the output, regardless of how much this guy changes, and my device is in active region?
Well, wouldn't Vout always be the same if you have VCC on one end of the resistor and then you've got, oh, never mind, your diodes.
Yeah, it's the other one.
Tell me, why should Vout change?
I mean, it's VCC on both sides.
Oh, because IC doesn't. IE or
Is
IC
VBE changing when
No.
VAC changes?
No.
Then your amplifier does not see your signal. Right? Because you put a voltage source here. Once you put a voltage source here, that voltage is fixed. The poor transistor doesn't even see the signal. All of your signal dies across that RB. It doesn't even get
Then put it on the other
to your transistor.
I don't
If-
think where
You try to be smart and remove RB, then I will kill you.
but that's not very.
If that guy doesn't kill you, I will kill you, because then you're going to damage that power supply, his power supply, and the transistor.
I don't agree there.
I feel like
So at least this RB is going to save your DAC. So these are examples of bad biasing, right? In here, you didn't turn on the transistor. In here, you can put the device in saturation. Even if you're careful, you may lose your signal. So that biasing and how to design the biasing network around your device is a really important topic.
Right there, the graph is run saturated.
We're going to focus on biasing for discrete circuits.
This thing.
So the difference between discrete and integrated circuits is that when I design an IC, transistors are the cheapest things I have. They're cheaper than resistors, they're cheaper than capacitors, they're the cheapest components available to me. So I use as many transistors as I can to avoid using resistors or capacitors or things like that, right? Discrete is the other way. Resistors and capacitors are cheap, transistors are a little bit more expensive. So, when you look at a circuit that is an integrated circuit, you see a lot of transistors and usually very, very, very few resistors, because resistors are expensive when you make integrated circuits. In IC design, area determines your cost, area of the chip. Resistors are big compared to your, for one resistor you can have 50 transistors. So if I can use 20 transistors to do my job, I'll use 20 transistors instead of one resistor. Discrete electronics is the other way. You basically have all of these available to you. Cheap devices, the ones that are not super special purpose, they're all about the same price. The transistors are a few cents, resistors are a few cents. So you use whatever that works best for you. If you need to use 2 transistors to bias one, you can, but you probably can do the same job with a few resistors as well. We're going to focus on biasing techniques that are applicable to mostly to discrete circuits. For integrated circuits, we sometimes use different circuits or techniques. Okay, so
Is that transistor?
let's do our first bias.
Oh, BJT's are transistor.
Yeah.
What do you think BJT stands for?
This is called simple
Oh,
bias.
T-FET, yeah.
Bipolar junction transistor. Because it has 2
And I'm going to show you circuits with NPNs. Same things, same principles apply to. So I have my resistor here.
Oh, I see.
So far I don't put anything in the emitter circuit.
Huh?
So let's say emitter is grounded.
Right.
Because BJT.
And simple biasing, okay, if you're rich or stupid,
You better not write math.
you go and pay for a voltage source here and a voltage source out there to do your bias. No, right? Because you can set your IB,
As long as the voltage is too strong.
and this gives you IC, and then hopefully you manage to get proper VCE by setting the proper value of RC. So VCE I'm not really too worried about. It depends on where in the amplifier chain you're putting this. I'm assuming the device is in IPH. So this gives you the IC that you want, right? And the price you pay is 2 voltage sources. You need the V bias here and you need the VCC there. You don't do it that way. So when you're making this circuit to sell something to people, you usually use the same power supply and you just choose the right value of RB to get the IB that you need, right? So if the bias was 2 volts and my VCC is, let's say, 4 volts, well, I can connect V bias to VCCs and use the same, just increase RB or adjust RB accordingly to get the IB dependencies. Right? So this is called simple biasing, and then the equation is really simple. So if I don't do that thing, if I use VCC for my V bias, so this is V bias equal to VCC, then I get beta times that, right? This bit is IB, and beta IB gives you IC. Anything wrong with this biasing? So remember, for biasing, and then I want to sell a million of these, right? So I want a circuit that is reliable, that is going to work, and I don't have to sell an engineer circuit. So anything wrong with this, do you think? In terms of biasing it, forget about the signal from the in terms of the stability of ICVCE that I can get out of it. What do you think is going to make my life a bit hard? Well, what are the parameters? Let's look at them one by one. VBE is a trusted friend, 0.6, 0.7 volts. That's not going to change much. Especially if I'm using the same transistor, a million of them will have, I don't know, a 50 millivolt variation in VBE for the same. So VBE, I'm not really worried too much about it. That's all good. RB, I can buy 5%, 2% resistors very cheap. And so RB again is not a big source of concern. Two other factors remaining. One is VCC, and the other one is beta. If your application is fixed, if you know what you're going to do, if you know, this is going to go into a radio, into a cell phone, into whatever, your VCC range is also fairly tight. 3 volts plus or minus 100 millivolts. It's not going to change that much. Your IC is not going to change that much with changes in VCC or VBE or RB. It's relatively stable when you look at those three, but it's super sensitive to beta. So if your beta is 100 or 200, it's going to change your current directly. You get 1 milliamp in one case, 2 milliamp in the other case. And that's bad news. Because how do I set my VCE over there? VCE over here is VCC minus RCIC. So I designed this circuit to be happy with 1 milliamp of current and a VCE of, let's say, 1 volt, when VCC is 5. If beta is doubled, my device will be in saturation for sure. Right? So you're going to have an angry customer. So, does the job done if you're making one circuit? And if you're sure that circuit is going to stay in this room, so the temperature is not going to change too much, all those things. Right? So if you're just playing at home, this can get the job done for you. But in general, especially if you're making a lot of devices, this is not a good way of doing it. What is the principle of this biasing technique? I'm setting IB, and I say IC is beta times that. Right? And I'm using this equation. I'm saying IC is beta IB. So by using this network here, I'm setting IB, and then IC is beta times that. This is how I bias the device, right? But kind of stinks. So let's find another way to bias. So I want to get a desired IC. How else can I do it? You may say, let's fix VBE, because we know from the equations that we had before. So this is voltage divided IC. Okay. So if I set VBE, then I get whatever I see the term on. Right? So if I know my transistor inside out, I can choose VBE and get IC. So here is the circuit that we propose. Some VBE knots, that gives you the desired IC. But at this point, you've seen a few of your colleagues, killed. So you don't pay for this. Right? So you go and say, okay, I need a voltage here that is this much. A cheap way of producing the voltage you like is to take a large voltage and use a voltage divider, a resistive voltage divider. Right? So what you do is that you do not use this. Instead, we say, you know what, I'm going to use the power supply that I already have. And choose the ratio of this RB2 and RB1 such that I get the desired VBE here. Right? So if you ignore IB, remember IB is relatively small. And if I choose the current through these resistors to be much, much larger than IB, so let's call this IB. And this is IB. So if I choose IBB to be much, much bigger than IB, then the voltage at this node does not depend on that IB anymore, right? I can simplify. I can say that the voltage at that node, VBE or VB at least, is equal to RB2 over RB1 plus RB2 times VCC. And if I know the current, I can calculate VBE I want, and I can choose the right resistors for RB1 and RB2 to get whatever VBE I want from any ECC you give me, right? And then you're going to get shot.
But not same numbers.
What's the problem with this
They
thing?
have like 0 to reverse bias.
So again, remember, biasing means that I put my device where I want it, reliably,
Not the answers.
right? So I set IC, I set VCE. I'd like this guy to stay there, not to be too sensitive. So this is great. It's not sensitive to beta anymore. Beta is gone. Beta sensitivity is gone. Or is it? I'll come back. But what is the type of problem you may have here? To see the problem a little bit more clearly, maybe think about the original circuit that came to mind first. And then you were smart to change it. So you lasted a few more minutes. But then what is wrong with this bias?
Recognize throwing a crazy amount of average out of your power source would mean that you need more power source.
So power source is an issue, right? But the issue with power source, and then I said, okay, I'm not going to pay for a 0.72 volt power source. I'm going to choose RB2 and RB1 so that I get 0.72 from 3, right?
But for that, your IBB has to be significantly larger than IB.
Okay, so IB is 10 microns. IBB, if I choose it to be 1 milliamp, I'm happy. It's 100 times larger. It's not that much more.
Would drain how faster?
You're wasting current. Right? So whatever current you use here, you're wasting because it's not helping you with amplification or anything. You're just setting the voltage here. So it is wasteful, but that's not the biggest problem. So, and then to see the biggest problem, look at this term. If the voltage at the base doesn't depend on the transistor current or whatever that is going on the right side, bad things can happen.
No RB.
So who remembers the diodes discussion? When you had a diode that was on, 1 milliamp of current going through a diode. You had 0.6 volts across it. The temperature went up by 1 degree. What happened to that VD on? There was a number, I'm sure I mentioned it. I can check the notes.
Yeah, your BTUs.
That voltage, the turn on voltage of the on voltage of the diode drops by about 2 millivolts. Right? So it's 2 millivolts per degree centigrade. It's actually reliable enough that you can make a temperature sensor.
Right.
2 millivolts per degree centigrade, right? Same thing happens here. You have a diode. 2 millivolts per degree centigrade. So, you make this circuit, you do all your calculations, you know you need 0.72 volts to bias this device where you want. You go and make the circuit, you call your boss in, you turn on the power supply and your device starts smoking. Why? Because as soon as you turn this guy on, it warms up a tiny bit. Let's say the temperature of the device goes up by 2 degrees. 2 degrees means that VDE on for a given current would be 4 millivolts less, but you fixed the voltage. So it has to be at 0.72 volts. What happens is that the current goes up, right? If you fix this voltage, this current has to go up with the larger IS because you're increasing IS, right? That's the temperature. So your current goes up. Your current goes up, what happens next? The transistor becomes
It's hotter.
Then what happens? The current goes up again. You have a positive feedback mechanism here. So this continues until your device is toast. Or your power supply doesn't have enough current to do it, but usually your device gets that. Right?
Big fan.
So you're delicate. If you folks look at it closely, if you go back to your circuit theory knowledge, you should say, well, you know, there's no difference between this and the previous one. Because I can use the Thevenin equivalent of whatever I have here, and it's just one resistor and one power supply. Right? It's the same as the one in here above, but there's a big difference between the two. Right? So for this, I can say R Thevenin for the resistors and V Thevenin for the equivalent circuit, and then the rest is here. For the linear part, I can use Thevenin and Norton, right? Because the linear part is linear. So I can find the Thevenin and Norton equivalent of that portion of the circuit and attach it back here. That's fine. And then you say, well, what is the difference between this circuit and the one here, which was super sensitive to beta? Why don't we have the same problem? The reason we don't have the same problem is that this RB is usually a large number here when you bias by setting IB. Over there, that's really, really small, right? And then you don't really see, basically the sensitivity is transferred instead of this RTH to this VT. You become sensitive to this instead of being sensitive to that. But anyway, so at the end of the story, this is a really, really bad way of biasing. So never ever do this. You can probably live a little bit longer with that. Never do this. This is a terrible idea. Okay, so let's see what else we can do. So far we have a couple of bad ideas. Yeah, one okay, and then one bad idea. Let me add one more resistor to this band circuit that I have. What was the problem? This VDE on this junction here is absorbing all of that. Okay? Let me add one resistor to this circuit. Let's see what happens. Let's put one resistor here in the meter circuit, and my and this is called the H biasing. And the reason for that name is that you have this thing that looks like an H. It's not. So those three resistors are used for bias. Analysis of the circuit should be easy by now. I can do it in a few different ways. You know, if you don't want to touch the circuit, you can write a KCL here and done. I'm gonna use my circuit knowledge and transform this into this. So this is the Thevenin equivalent of the circuit in the base.
Yeah, that's fun. It's like, it's usually funny here. There's a specific situation, but it's funny.
Yeah.
And this is almost bad.
Okay.
I think there's
the circuit for the two resistors in the base plus the power supply at the top.
Go for it.
I put the Thevenin equivalent circuit, and now this is familiar. We've done this many times. You can quickly write a KVL in this loop, and you're done. So your Thevenin source VCC times RB2 over RB1 plus RB2 is equal to RB1 with RB2. So this is my R Thevenin, and this is my V Thevenin. Times IB. I'm using the constant voltage model that's going to be accurate enough, plus IB. Right? Assuming active, VB is about 0.657 volts, I make sure VC is about 0.5, 0.6 volts or more. And that's it. I can find IC in one shot.
That's a great thing.
Okay? And if you choose the values, well, okay, what does that mean? Meaning that if you set the current here through these two resistors, this is called IBB. If you make sure IBB is much larger than IB. What is much larger? It depends on your power budget, how much money you have. If I cannot afford a lot of current, 5 is a large number. If I want to be relaxed, maybe 20. Right? So IBB, the current that I choose to flow from VCC to RB1 and RB2, I choose it to be 10 times, 20 times larger than IB. What way to bias currents? Right? You know what is IB. Because you choose IC, you know better. So if you choose IBB that way, then this VTH is almost constant. The voltage drop or the voltage at the base of the transistor is almost constant. If IB changes a little bit, it doesn't affect the voltage at that base. That's almost constant. VBE is almost constant. Beta was my variable, right? But I can choose RE such that the effective variations of beta become less significant. All I need to do is to make sure RE, because alpha is more or less 1. So don't worry about that. All I need to do is to make sure this R Thevenin, the combination, the two resistors in parallel, divided by beta, which is a large number, is smaller by margin. That again depends on you. So maybe 2 times, 3 times smaller than R. If that's the case, then a 50% change in beta is not going to affect my bias current that much. Alpha doesn't affect it that much, and then I have a very stable bias. Right? So this is called H biasing. For discrete circuits, this is our favorite biasing method. There's one more that does more or less the same thing using one resistor. I'll talk about that next week. But once you choose IC, you need to choose your VC or set your VCE, or because you now have an RE here, the voltage at the emitter is not 0 anymore. It's IE. So let's say this is 100, 200, 300 volts, that's ohms. You have a few hundred millivolts of it. And then you put enough VCE on top of this to make sure this device is not super close to saturation. Sorry, we went over time by 2 minutes. So 2 points to remember when you're designing with H biasing. 1, choose IBB to be much larger than IB. You know IC, you know your beta, you have a feeling for IP. So much larger means 5x to 20x. Right? More than 20x is you're wasting your money. So that's one. Two. And you know, somebody at the beginning of next lecture asked me, forget about the equations. How does that resistor do this? How does that one resistor make life so beautiful? That this thing is not sensitive to a lot of other parameters. So somebody, think about it, but somebody at the beginning of next lecture ask me, or tell me why that resistor is doing that magical thing. But the second thing you do when you design this network, call this VRE. You set VRE to be somewhere, if you're constrained by the power supply, about 100 to 200 millivolts. If you have no worries, all the way to 500 millivolts or so. More than that, you really don't get much gain. So you know IC, if you want to put 500 millivolts across that RE, IC and RE are more or less the same, you get RE right away. You have your RE, you have your VRE, you know the voltage here. You know IB, you want IBB to be, let's say, 10 times bigger, and you know the voltage here, the voltage division, you already know it. The ratio of these two resistors should give you the voltage that you want here. You can choose those two resistors. Right? So that's the design cycle. You assign some voltage to VRE, 200 millivolts is usually good enough if you can afford it, 500. Then you have a voltage here. Choose RB2 and RB1 such that you get the voltage you want. But that's two unknowns, one equation. The second equation comes from choosing IBD. So you say, I choose this to be 10 times that. That gives you RB1 plus RB2. And then you know the voltage here, that gives you, what is it, this ratio. You have all the design parameters for your policy. So, sorry, you went 5 minutes over
it
got
got
Next time you don't take a break.
Is this gonna be on the quiz tomorrow or not tomorrow? Friday?
Sorry?
Is this gonna be on the quiz?
PC.